right, so if there are no issues, I'll start. Thanks everyone for attending. I'm Emaad. I'm a PhD student at CMU, and I'm going to talk about our work on taxonomy expansion. This is joint work with Dhananjay, Ray, and Jure at Pinterest. Let's first talk about what do we mean by taxonomies. We define taxonomies as a collection of related concepts. Concepts could be anything from geographical entities to musical genres to products. And they're structured as a directed graph, where the direction of each edge goes from a child to a parent. What makes taxonomies different from general directed graphs is this notion of a hierarchy. This notion is formalized by something called the distributional inclusion hypothesis, which says that a parent is connected to a child if it is both related to and more general than the child. And this is what brings encodes this hierarchy. We also assume that each node is associated with some feature vector. In the case of textual taxonomies, this could be word embeddings. In the case of multimodal taxonomies, it could be a combination of word and image embeddings. Taxonomies have been used to improve the performance of several downstream tasks by encoding some kind of structured knowledge. Some examples are classification, recommendations, information retrieval, and user modeling. Now let's look at how they're used in the specific case of Pinterest. The Pinterest taxonomy, which I'm visualizing in this animation on the right, is a hierarchy of interests of users on Pinterest. Some examples of interests are clothing, art, food, and drink. And these interests are used across Pinterest to both target ads and to recommend relevant content to users. The Pinterest taxonomy is a tree-structured taxonomy with around 11,000 nodes. It's 7 levels deep, and it's 100% expert curated. While expert curation makes this a very high-quality taxonomy, it comes at the cost of significant effort and time. To give you a more concrete idea of the effort required, here are some numbers from a paper last year on expanding the Pinterest taxonomy manually. According to this paper, 8 curators took 1 month to add 6,000 nodes, which boils down to a few minutes of effort per node. Compared to the rate at which new content is added to Pinterest, which is at the rate of billions per second, it's clear that manual expansion is going to be too difficult to scale. And this is what motivates our problem. What we want is a method that, given a taxonomy with features for each node, and given an unseen query queue with a feature vector that's not a part of this taxonomy, we want to rank all the taxonomy nodes such that the true parents of Q are ranked high. Since we expect this method to be used with humans in the loop, we also want the predictions to be easy to verify. So an additional requirement for us is we want the predicted parents to be near the true parents in the taxonomy in terms of the undirected shortest path distance. Such predictions are easier to fix because the true parent can be searched for in a small neighborhood around the predicted parent instead of searching the entire taxonomy. Why is this hard? The first challenge in taxonomy expansion is this issue called lexical memorization. It was first reported by Levy and co-authors in 2015. They were studying hypernym detectors, which are binary classifiers of whether a node pair is indeed a child-parent pair. And what they found is that if there are certain parent nodes with a large number of children, hypernym detectors simply learn to detect these prototypical parents instead of actually capturing taxonomic relationships. The second challenge that's specific to our setting is that edges can have heterogeneous semantics. So for example, in the Pinterest taxonomy, outgoing edges from a geographical node are more likely to have is-in semantics, and outgoing edges from an occupational node are more likely to have is-a semantics. And these semantics are unobserved, which makes it even more challenging to model. And we don't want to burden taxonomists with providing us these edge labels in addition to organizing the taxonomy. We instead want to learn the implied semantics from the way taxonomists organize these concepts to serve business needs. The third challenge is the need to make predictions for humans in the loop that are easy to verify, and this is something that has not been considered in previous work. So now I'll talk about our solution in 3 steps. I'll first describe how we model taxonomic relatedness. Then I'll talk about how do we learn this model from the data with some theoretical guarantees on the ease of human verification. And finally, I'll describe our evaluation setup and results. how do we model taxonomic relatedness? We want to come up with a relatedness score that is learned from the child-parent relationships between the feature vectors in the taxonomy. A simple way to define such a score comes from metric learning. We can learn a matrix M from the data. This is a transformation matrix, which when applied to the child feature vector, makes it similar to the parent feature vector in terms of the dot product. The problem with this scoring function is that it assumes we use the same transformation matrix for all edges. And we need something more flexible if we believe that edges can have different semantic meanings. A very flexible alternative is to give each node its own transformation metrics. So in this way, each node can determine the semantics of its own outgoing edges. So that's the node local linear map here. The problem with this formulation is the explosion in the number of parameters. So the number of parameters shoots up to the order of d squared v, where d is the dimensionality of the feature vector and v is the number of nodes in the taxonomy. What we propose instead is a formulation that's somewhere in between these two extremes. So in our formulation, the score function remains the same, but we formulate the transformation matrix as a weighted linear combination of k linear maps. So let's parse this equation now. So we're modeling the transformation matrix of a single node V in terms of k latent edge semantics, where k is a hyperparameter, and pi is the linear map associated with each semantic type. The weights of this linear combination are given by this vector wv, which you can think of this as the taxonomic role of node v. And putting this to, since we expect similar nodes to have similar outgoing edge semantics, we in turn define this taxonomic role as a learnable function of the node's feature vector. And that completes the specification of our taxonomic relatedness score. The parameters we need to learn now are the k linear maps and the function f that maps node feature vectors to their taxonomic roles. And f could be anything from a simple linear transformation to a neural network. In contrast with the more flexible score we saw earlier, this requires learning much fewer parameters, and it also allows nodes to share information with each other, which makes the method more robust to noise. Okay, now we'll talk about how do we learn this model from the data. We're going to train this model by minimizing a large margin loss that's very similar to the triplet loss that's used in computer vision. So formally, what we want is we want the score of a true child-parent pair to be greater than the score of a non-child-parent pair by some margin gamma. This is a desired constraint. This constraint is violated if the converse happens. And we can quantify the degree to which the constraint is violated and use it to construct our loss function, which is essentially this constraint violation summed over all triplets of child, parent, and non-parent nodes in the taxonomy. But how do we pick this margin gamma? The easiest way is to assume some sort of constant and pick it heuristically, something like 1 or 0.1. A more principled way is to tune this constant to the validation set. And these two options are right now the most popular ways of picking margins. There are some ways to learn this margin from the data. It becomes a part of the training process. What we do instead is to propose dynamic margins, which are motivated by certain theoretical guarantees. So concretely, what we do is we define the margin as a function of the triplet. It varies across triplets, and that's what makes it dynamic. We set the margin to the shortest path distance between the true parent node and the non-parent node of the triplet. And intuitively, this makes sense. If the non-parent is far away from the true parent, we want the margin to be large. And if it's nearby, we're okay with the margin being small. But we can also show that if you define the margin this way, then the loss function is in fact an upper bound on the sum of the shortest path distances between the true parent and the predicted parent. And this result is useful because it guarantees that the predicted parents will be near the true parents in the taxonomy if the guarantee holds in expectation. In practice, it's infeasible to sum over all possible triplets, so we resort to negative sampling. very similar to skip-cram negative sampling when you're training word embeddings. So we sample a fixed number of non-parents at random for every child-parent pair. The issue with negative sampling combined with this large margin loss is that the loss very rapidly drops to zero. As the training progresses, there'll be very few non-parents that violate the margin constraints, and the loss drops to zero too quickly. To prevent this from happening, we use something called distance-weighted negative sampling, which was proposed a couple of years back, which promotes sampling hard negative samples, and that prevents the loss from dropping to zero too quickly. There are a bunch of other implementation details that I'm not going to talk about, but please check out the paper for all the details. And now we can move on to the evaluation. So we evaluate our method on 3 textual taxonomies with different characteristics. The first is our gold standard curated taxonomy from Pinterest. It has heterogeneous edge semantics, and the nodes can be either concrete entities or abstract concepts. We use the pin text embeddings for each node as their feature vectors. These are a type of word embeddings that are tailored to Pinterest content, which was we talked about in a KDD paper last year. The second data set is an automatically constructed taxonomy that was used in the SemEval hypernym discovery shared task. So importantly, this taxonomy was automatically constructed and validated by humans. It was not curated by taxonomic experts to serve any specific business need. So that makes it very different from the Pinterest taxonomy. It has homogeneous edge semantics, and we use the fast text embeddings for each node as their feature vectors. The third dataset is a heterogeneous taxonomy extracted from the WordNet graph. It has 3 known edge types, and we use the fast text embeddings as the feature vectors for each node. We hold out 15% of the leaf nodes and their outgoing edges as a test set, and we use the remaining child-parent pairs for training. And we evaluate each method on 3 metrics: the mean reciprocal rank, which measures ranking performance; the recall at 15, which counts how often the true parent lies in the top 15 predicted parents; and the shortest path distance between the top ranked predicted parent and the true parent in the taxonomy, which measures the ease of human verification. So now we're going to look at 3 evaluation experiments. First, we ask, can we repurpose hypernym detectors for taxonomy expansion? So recall that hypernym detectors are just binary classifiers of node feature vectors, which classify whether a node pair is taxonomically related. So what we do is we measure the classification F1 scores of 4 hypernym detectors on our datasets. Each hypernym detector uses a different vector operation on the feature vectors, followed by a random forest classifier. We train the hypernym detectors on a balanced dataset, where for each child-parent pair in the training data, we randomly sample a non-child-parent pair to match. If you look at the F1 scores, we can observe 3 things. The first is that the classifiers perform reasonably well, in spite of being fairly simple. The second is that using a domain-specific embedding like pin text significantly improves performance over a generic embedding like fast text. So this should be taken into consideration if you're deploying an automatic taxonomy expansion method in practice. And the third is that there's no hypernym detector that dominates for all 3 data sets. And this suggests that there's probably some more complicated vector operations needed to capture taxonomic relationships. Now, if we look at the ranking performance by the 3 methods, we can see that the hypernym detectors appear less promising. So the first thing to observe is that the relative ranking performance does not match their relative classification performance. So one task cannot be used as a proxy for the other. And overall, all this goes to say is that there could be a significant benefit from explicitly formulating taxonomy expansion as a ranking task instead of trying to repurpose a binary classifier. So now let's look at taxonomy expansion performance. And we want to answer the question, does explicitly accommodating heterogeneous edge semantics help? We compare a method against CRIM, which is a method designed to model homogeneous edge semantics. It optimizes a loss function that is very similar to the skip-cram negative sampling loss. And what we find that in terms of for the ranking performance, we find that if the taxonomy has heterogeneous edge semantics, the performance gains from using our method are significant. So our method is 5 percentage points more better on the Pinterest dataset, and 8 percentage points better on the MAML dataset in terms of the mean reciprocal rank. When the taxonomy is homogeneous, the gains are less. And for homogeneous taxonomies, any gains we see are coming only from the large margin loss function, which is more robust to overfitting and noise than the skip-gram negative sampling loss function. If you look at the shortest path distance metric, we see a similar pattern. The predictions from our method are easier to verify by humans when the taxonomy has heterogeneous edge semantics, because it predicts parents that are closer to the true parents in the taxonomy. Now let's take a closer look at the predictions that our method makes on the Pinterest taxonomy. So this table has the top 4 predicted parents for 5 random test queries. And we can see that our method has picked up different types of semantics. So this Luxor query is a concrete entity with is in semantics. And the depression query is an abstract concept with is type of semantics. In the spirit of transparency, let's also look at test queries where our method did not do well. So these are the top 4 predicted parents for test queries where the true parent was not in the top 4. And what's interesting to see here is that even when it failed to rank the true parents high, the predictions appear to be taxonomically valid. So all the predicted parents are related to and more general than the query. And finally, to make sure that there's no data leakage, so we want to make sure that the feature vectors are not leaking information from the taxonomy. We also make predictions for Pinterest search queries that are not present in the taxonomy. So all of the queries here are not present in the taxonomy in any way. And you can see that the results make sense. The results are taxonomically valid even in this case. And one result I want to point out in particular are the predictions for this phrase, what causes blackheads. Our method thinks this is a subclass of skin concern, which makes sense. It also believes it's a subclass of feelings, which makes sense at a deeper level because the search query is an expression of concern. The paper has a bunch of more experiments, including an ablation study and a study on the impact of parameters and some preliminary results on inferring taxonomic roles. But I'm not going to discuss that in this talk. And with that, I conclude the talk. To summarize, we've seen a new method to automatically expand taxonomies with heterogeneous edge semantics that is tailored to human-in-the-loop verification. And our approach relies on 3 key ingredients. The first is modeling the latent edge semantics using taxonomic roles with linear maps. And the second is our large margin loss function with dynamic margins. And the third and final ingredient is our theoretical guarantee of easy human verification. And with that, I'll stop. You can check the website for code, slides, and a video of this talk if it's going to be made available. And I'm happy to take questions.
Hello, Iman. Can you hear me?
Hi. Yes, I can hear you.
It was a nice presentation. My question is a very basic one because I'm not an expert in this subject. But for taxonomy expansion, what would be the input? I mean, if I want to use this work for other sort of knowledge knowledge graphs, then is it possible to use this kind of work to, let's say, predicting entities that are not in the knowledge graph, or I'm totally missing the point of the paper?
Yeah, so let me get to that. So the input that we require is the following. You have a taxonomy with nodes and edges, and you also have some feature vector for every node. You could have the word embedding or the image embedding. Given this taxonomy, what you can do is if you see a new node with a feature vector, this method will tell you where should I attach this node to the taxonomy.
Mm-hmm.
Now, extending this to knowledge graphs with unseen entities is something that could be done, but it's not something that we've considered here. Simply because the way knowledge graph embeddings are trained is they are trained on the knowledge graph itself. So the way we talk about this in the paper. The way knowledge graph embeddings are trained right now, I don't know if there's a way to get the embedding of an unseen node. And this paper doesn't talk about creating the embedding of a node. It assumes that you have the embeddings.
Yeah.
Does that answer your question?
I think yes. Yeah, I just wanted to see if there was a link between this and the knowledge graph embeddings, and I think it's clear that you already have the embeddings, and there is hierarchy, and that's why it's possible.
Yes. There is a link, but this doesn't solve that problem. So that's a good direction for future work.
Thank you.
May I ask you a question? Can you hear me?
Sure.
On the one of your last slides, you have a plot of word embedding space, I guess, with some clouds of words. Is it based on fast text embeddings or?
This plot?
Just a second. No, not this one.
So if you're asking about what embeddings we use,
yeah, this one.
Okay. This is based on fast text embeddings for the mammal taxonomy.
Okay. My question is, it looks like the space is not that clustered, and is it the right embeddings to use this for this task? I mean, maybe it's better if the words are a bit clustered and you can use centroids for detecting hyponyms.
Okay, so this plot was from an experiment that I didn't talk about. So what we were trying to do is, could we figure out the role of a node in an unsupervised manner, simply using the taxonomy. So that's what this plot is about, and these are very preliminary results, so we don't have a definitive answer to that question. And yeah, coming to your question of could we use better embeddings, better embeddings will definitely improve performance. So, but this method takes the embeddings as a plugin. You can use any embeddings you want, and depending on how good they are, you will get better performance.
Sounds good. Thank you.
Thanks.